Alright, so here we have a block of mass M. It is initially released from rest at point A, and it's going to make it through this loop-the-loop, vertical loop. In part A, B, C, D, and E, asks you to find these quantities, pause it, read it. Alright, I'm just going to go ahead and do it. Part A asks you to find the minimum height at which it can start from rest and still make it around the loop. So my starting point would be at the very top of the ramp here at point A. And then my final reference frame for part A will be at the very top of the loop. So keep that in mind. So initial and then final is at the top of the loop. So I'm just going to set up conservation of mechanical energy. It says frictionless, so mechanical energy must be conserved. So MEI must equal to MEF. I'm just going to break up MEI and MEF down to their respective energies. There's PI plus KI and then PF plus KEF. Here I'm just going to cross out KI because it says starts at rest. And now I'm just going to expand PEI into MGHI and then PF into MGHF. Keep in mind, once again, HF here being at the very, very top of the loop. Okay. KF here is just 1/2 MVF square. As you can see here, mass cancels out. It appears in every term. The only thing that I have to really figure out is VF square, which I highlight in yellow for you here. Right. I'm trying to find HI. Here, I know what HF is. HF is just going to be 2R because well, the diameter of the circle here would just be 2 times the radius. So HF here would just be 2R. But because part A says the minimum height, here's my f of g at the top of the loop. Okay, there is no f of n because you're trying to find a minimum value. So it's assuming just right at that critical point where it's about to lose contact. So we just assume that f of n is equal to 0 because it's about to lose contact with the track. So at the very top of the loop, the only force acting on it is f of g. And this is only true because it says minimum height. So it's important that you don't do this all the time. Only do the strategy when it uses the term minimum height, because anything greater than that will make it all the way through. Okay, so I'm just going to set up the centripetal force at the very top of the loop. At the top of the loop, the only vector pointing towards the center of the loop is this f of g. So I'm going to say f of g is f of c, or f of c is f of g, however you want to say it. Here I'm just going to break up f of c, which is mv squared over r. F of g is m times g. As you can see here, mass cancels out. And then to solve for v squared, because that's what we need here, on the right side of my work, again, I'm missing vf squared. So therefore, I'm going to find what the vf at the top of the loop here is by using the centripetal force. V squared here is going to get, or in order to get v squared by itself, I would just multiply both sides by r. So v squared here is just gr. So once I know v squared, I'm just going to plug it into my highlighted yellow to the right side here. So I'm just going to carry my work down. G and H on the left side, the equal sign stays the same. Once again, HF is 2R because from the bottom all the way up to the top is a distance or a height of 2R because it's the diameter of a circle, which is just 2 times the radius. And then VF squared got substituted out for G and R. Keep in mind this is V squared by itself already, so don't square root it and then having to square it again, but it's up to you. All right, here I have 2GR plus another half GR, which is 2.5 GR. So G is going to cancel out anyways. So here, HI is just going to equal to 2R plus a half R. Okay, so 2 plus a half is 2.5 R. So that is our answer. So the minimum height required will be 2.5 times the radius. All right, that is the answer to part A. Let's do part B. Part B here asks you to derive an expression for the magnitude of the contact force at point B. So once again, at point B is the lowest point. I'm just going to go ahead and draw my vectors out. At point B, here's f of g pointing down. Here's f of n pushing up on the block. Here, Fn is going to be a little bigger. F of g is going to be a little smaller because you need this particular force to, quote unquote, keep the system moving upward. Here, f of c is going to equal f of n minus f of g. Fn is pointing up, f of g is pointing downward, so you would just subtract. And then here, I'm just going to go ahead and break f of c into mv squared over r. And the right side stays the same. And then keep in mind, the question asks you to find f of n. Okay, so here, to get f of n by itself, I'm just going to go ahead and move this negative f of g to the left side, which changes sign. So here we have mv squared over r plus f of g. Well, once again, I can substitute out for f of g. F of g is super light work, right? It's just m times acceleration due to gravity. But here, I don't know what v squared is. Okay, well, at the bottom, I know it's going to pick up speed and it's going to, move fastest at point B here. So what I can do is I can set up conservation energy. The block initially starts at point A and it's going to slide down a frictionless ramp and it's going to get to point B. So all of this mechanical energy at the very top will be converted to mechanical energy, or excuse me, will be converted to kinetic energy at point B. So I'm just going to bypass a couple of lines here. I'm just going to say the initial gravity, the initial potential energy due to gravity is equal to Kf, which is at point B. So all of this PE that's stored in the system will be converted to Ke at point B, because at point B, it is the lowest point, so there's no height. All right, other than that, I'm just going to say PEI is equal to mghi. Kef is just 1/2 mvf squared. Once again, mass cancels out here. And then here, to get vf squared by itself, I would multiply both sides by 2. So hence, I'm just going to move the 2 in the denominator on the right side up to the top left numerator. So 2ghi, but hi we already found in part A, which is 2.5 times r. So here I'm just going to substitute out hi for 2.5 r. So as you can see, 2 times 2.5 will give us 5, and then that'd be 5gr. So vf squared itself will equal to 5gr. Well, now that we have vf squared, we can just substitute it out. Okay. So here in this work, when I set up centripetal force, I was missing v squared. Well, I just found v squared using conservation of energy from point A to point B. So now I can substitute out v squared. So here, instead of v squared, I just substituted out for 5gr because I just found it. And then from there, you can just go ahead and cancel out r here in the first term. There's an r in the numerator, r in the denominator. So therefore, this would just be 5m times g plus mg. So 5 plus 1, which is be 6. So the answer would just be 6mg. Okay, so that'd be the magnitude of f of n at point B, the lowest point. All right, let's do part C. Oh, I forgot. I made a note here. The apparent weight, which is f of n, will always be greater than f of g at the bottom loop. Okay, so keep that in mind in case you get a conceptual question. All right. Here, part C asks you what is the kinetic energy at point C using H found in part A. Well, point C is right here. It's not exactly at the bottom or the side, so you have to do a little geometry here. All right, so to find Ke, I'm just going to set up conservation of mechanical energy again. All of the mechanical energy at point A will be transferred or converted to energy at point C. Okay, so at point C, though, it is off the ground, so it has to have a PE, and it's still moving, so there is Ke. So I'm going to go ahead and break up MEI and MEF once again. Kei cancels out. And then PEF and KF I'm going to keep because both those terms exist at point C. All right, point C is not at the lowest point, so it has the height. Because it has the height, it has to have a PE. And it's moving, so it has to have a KE. But here, part C asks you to find what is KE at point C. So unlike the other parts, I kept KEF as the unknown because that's what I'm asked to find. So don't break it up into 1/2 mvf squared. Okay, so KF stays, and then here, I already know HI is 2.5 R from part A. Here I don't know what HF is. So at point C, I can find HF really quick. And keep in mind, HF is measured from ground up. So here, follow with the geometry. This is pretty quick and painless. The radius here is R, right? I can find this leg right here, this vertical height, because here's R. That's the vertical leg. Here is 30. So this leg here is the opposite leg, which is sine. Sine of what? Sine of the hypotenuse. In this case, that'd be r. So this leg here, which is be r times sine of 30. But sine of 30 is just a half. So I just multiply by half, or you can say r divided by 2, however you want to say it. Now, well, watch my cursor. From the ground all the way up to point D, that is just the radius r. Well, if this blue leg is already half r, the remaining distance would just be another half, because a half plus a half is a whole. So from ground up, from the ground to point C, is just r over 2. Because this black segment here, which is r over 2, plus this blue segment, which is r over 2, 1/2 plus 1/2 makes 1, which makes sense because this is just 1 radii. Okay, so HF here is just r over 2. So I'm just going to substitute out HF for r over 2. And then here, you notice here I have KF, but it's not by itself yet, so I'm just going to do a little manipulation here. So I can just say that 1/2 here is just 0.5, which on the left side, but it's positive, so I'm going to move it to the left side to combine like terms, so that makes it a negative sign. Okay, so therefore 2.5 mgr minus 0.5 mgr would just give you a difference of 2 mgr. So that is your answer for KEF. So that's your KE at point C. All right. Let's go ahead and do D. D asks you to find or derive an expression for the magnitude of the centripetal force at C. Well, to find the centripetal force at point C, we can just go ahead and set up F of C is equal to mv squared over r. Well, to find F of C, I need mass, I need r, and I need v square. However, what I do have though is the statement that I saw for in part C. Okay, I know that the KE at point C is just 2 times m times g and whatever r is. So I'm just going to carry that statement over here. 2 times m times g times r is equal to KEF. What I can do now is I can break up the right side into 1/2 mvf squared. So this vf is the v at point C. Okay, so if you look at this carefully, there's an m on the left side, there's an m on the right side. I'm just going to cancel those two out. And then to get vf squared by itself, I'm going to multiply both sides by 2. So 2 times 2 here will give me 4. So this will be 4 times g times r, which is equal to vf squared. But the centripetal force term is mv squared over r. So I'm going to substitute out v squared. So I carry down this work here. So f of c is mv squared over r. But v squared I can substitute out for 4gr because I just found it to be. Okay, and as you can see here, r on top, r on the bottom will cancel out. So therefore, the centripetal force at this particular location will have a magnitude of 4mg. So it would just be m times 4 times g, which is the same as 4mg. I just pull the coefficient on the front. All right. Other than that is the answer to part D. Okay. Let's do part E. Part E says if m is 2 kilograms, find the magnitude of the net force at point D using h found in part A. So we know it's going to make it all the way around barely. So here's point D, which is on the side, which is the distance of r above the ground. So to find this net force, you have to go ahead and draw your free body diagram. Here's f of g pointing down the page. But at point D, though, the normal force for location D will be pointing inward, or to the left in this case, because this is the force exerted by the track onto the block. So that's f of n. But you notice here in part E, it didn't ask you to find Fn or Fg, it asked you to find net force. Well, here you have a vector pointing down, you have a vector pointing left, so therefore the net force would be some vector pointing down and left. Okay, so I'm not drawing a scale here, but the direction of your net force should be in the southwest corner, or down and left. So here's your net force. I need to find this. So what I can do is just apply Pythagorean theorem because it's just a right triangle. Here I can say net force square, or this is just really Pythagorean theorem. A square plus b squared equals c squared. So here my net force being the hypotenuse, so net force square is equal to f of n squared plus f of g squared. Here I know what f of g is. F of g is mass times gravity. What I don't know is f of n. So what I want to do is I'm just going to go ahead and find f of n at point D. Okay. But at point D, f of n is just the centripetal force, or we say the centripetal force is f of n, because at point D, the only vector pointing towards the center of this loop-the-loop is f of n. So therefore, I can break up f of c into mv squared over r. I need to find what f of n is, but, well, I know what m is, I know what r is. These are just variables given in the diagram, right? This is m and this is r. Whatever the values are, we can substitute in later. Here it says m is equal to 2 kilograms anyways. What I can do, though, is I can set up conservation of energy to find v squared. Okay. So here at point D, the object is moving. It is a height off the ground. So I'm just going to say whatever PE is at point A, that'll be distributed or dispersed into PE and KE at point D. So PEI here being at point A in the diagram, PF and KF being at point D. So I'm just going to say MGHI equals MGHF plus 1/2 MV squared. But I need to find V because I need to find Fn. Once I find Fn, I can plug it in the Pythagorean theorem and call it a day. All right. So here, mass cancels out. Okay. Now, HI, we find in part A, which is 2.5 R. HF here is just R. Okay. So as you measure stuff, measure correctly. From ground to point D, that is just a distance of R. So that's why HF is just R. So this is GR. This is 2.5 GR. So I'm going to go ahead and move this term GR to the left side by subtracting it. So 2.5 minus 1 is 1.5 GR. And then this is still 1/2 VF squared. And then to get VF squared by itself, I will multiply both sides by 2. And that'll make 1.5 times 2, which is 3, times G times R. So now I know what VF squared is. I can substitute it out here in the centripetal force function to find Fn. So here, M got carried down. V squared, the whole term, is just 3 times G times R. And then R cancels out. So therefore, F of n in this particular location is just 3mg. But once I know that, I can go ahead and plug values in. because it says M is 2. I know G is 9.8. So here's 3, M is 2, G is 9.8. So the magnitude of F of n is going to come out to be about 58.8. Well, now that I know that, I can just plug it into the Pythagorean theorem. Okay, so F of n itself is 58.8, and don't forget to square that. And then M being 2, G being 9.8, 2 times 9.8 is 19.6. I'm going to square that. So really I'm just doing Pythagorean theorem here at this point. So if you do it correctly, on the right side, once you square everything and add them, you should get 3,846.6, and then take the square root of that, and then your final net force will have a magnitude of 61.98 newtons, and that's the answer to part E. All right, stay nerdy, don't be whack.